All right, so what did I just say? 32. All right, so here's the deal with 32. So you've got this wheel, and it's rolling, but it's got like an axle on it. So it's rolling like that, right? Okay, and what it tells us is that it's got a large radius of 0.4 meters, and the radius of the axle itself, I'm going to call that little r, that's 0.2 meters. Okay? Now, it is smooth rolling, but it's not smooth rolling about its perimeter, which is why we can't use the beta KE thing. Okay? So here's what else it tells us. It tells us that the wheel-axle combination has a mass of 10 kilograms and a rotational inertia of 0.6 kilogram meters squared. The wheel's initially at rest. So up here, our omega is 0. And it's going to roll down a length of 2 meters. It tells us this angle here is 30 degrees, right? So my drawing is about to get cluttered here. So this distance here is 2 meters, which means at the top, my height is just 1 meter, right? Yep. Everybody cool with that? Because it's a 30, 60, 90 triangle? Okay, so, I mean, the problem guides you. I mean, you're looking for stuff about energy. What should be true about the energy as it rolls down, you guys? Should be conserved, right? The total energy should be the same at the top and the bottom, right? So, total energy top equals total energy at the bottom. So at the top, we've got GPE. So that's mgh, right? Equals total energy at the bottom. What types of energy do we have at the bottom? KE and RKE, right? So the KE is 1/2 mv squared. And then here's the deal. Your RKE, again, you can't just use beta times KE. Because what would beta even be, right? Somebody commented that you could sort of use... Well, I wonder if that works out. Well, there's one of your sheets has an equation for a hoop with thickness to find the rotational inertia. I don't remember what the equation is off the top of my head. I wonder if this corresponds with it. All right, anyway, because it's not smooth rolling, you can't do beta times KE. I'm sorry, it's not rolling about the perimeter. So we got to do 1/2 I times omega squared. Follow? All right, so it doesn't look like anything's going to cancel. So I think I'm going to just start plugging in numbers. Okay? So here we go. So we get, what's the mass? So you get 10 times 9.8, so that's going to be 98 times 1, so you get 98 joules equals 1/2 times the mass is going to be 5v squared plus, so 1/2, our I is 0.6 times, I gotta figure out a way to deal with this W. So yeah, W is V over R. Which R? This is like the one thing that you gotta be careful of.
Would it be, yeah, would it be careful of?
It's the smaller one. Because it's rolling about this smaller radius.
Oh, okay.
Right?
Yeah.
And so that's where it's smooth rolling at that point. So that's where the connection between your linear and your angular occurs. Okay? So it should be V over, oh shoot, I wanted this to be green, 0.2 squared. Follow? Oh shoot. I'm glad we went over this because I realized, dang it, I've got my answers flip-flopped. So if that's why you struggled with this, it's, so you get that. So from there, do you guys all agree you can solve for your velocity? All right, so when you solve for the velocity, you get, I just had the sheet with my answers on it a second ago. And I set it down somewhere stupid like I always do. No, it's a white piece of paper. What is it? 2.8. We'll go with that. That sounds right. That rings a bell. Okay, so 2.8 meters a second. And now I can go back in and plug in my velocity to find my KE and my RKE. So this one is the KE. This one is the RKE. Okay, they turn out to be 39.2 and 58.8. On the sheet you guys have, I have those flip-flopped. I have since corrected it, but that doesn't help you any. Cool? Joules. J for joules. What's energy? Solve for V and plug it back in. All right, are we good with this, you guys? All right, so bell's gonna ring. I don't know that I have time to do another one.